Yes, so the recording has started. Uh, Vignesh, you would like to take over?
No, we'll start.
Okay, so we are starting the session now, guys. So we'll be solving the PYQs for the maths too. Okay, so let's get started. I'll share my screen and just let me know whether the screen is visible or not. Is it visible?
Yes.
Yes, sir. It's
So we are solving the paper of the previous term, this which was held on October 27. Let's start. The very first question here is quite theoretical. So I'll just take a screenshot from here, paste it here. Okay, so here we go. So you need to read the options and tell us which option is correct. So we are starting with the very first option that says A and B are two matrices of order n cross n. Means it says A and B both are square matrices. So whenever you see this M n cross n R, so this means it is a subspace containing all the space containing all the n cross n matrices having the real values. Okay. And additionally, it says that AB is equal to 0. The product of both matrices is equal to 0. And then it says that at least one of the matrices A or B must have the determinant 0. If this condition is given to you, then whether it implies A or B must be determinant must have the determinant 0 or not. That is your first option. So what do you think? What should we do? What should we do in this case?
Take both
I
side
think we should.
determinant.
I think we should choose the correct options.
Oh, great. So whenever we have a situation like this and we want to talk about the determinant of one of the matrices, so the best option here is to take determinant on both sides. Given AB is a square matrix, so we know A is a square matrix, B is a square matrix, so their product is also going to be a square matrix. So we can take determinant on both sides. So determinant of AB is equal to determinant of this zero matrix. Okay, so if both are matrices, then on the right hand side you'll also get a matrix. So that's why it's zero matrix. So the determinant of zero matrix is going to be 0 only. And here it says the determinant of A times B is equal to 0. Now what can I do? So one property you need to keep in your mind, that if determinant of AB can be written as determinant of A times determinant of B, given both A and B are square matrices. Okay, so if both of these determinants are defined, and determinants are defined if both matrices are square matrices, then you can write something like this.
Sir, is this only for a square matrix or for even equal sized matrices it is possible? Like let's say 3 by 3, is it also possible?
Okay, 3 cross 3 is a square matrix, correct? If
Uh,
non, if you
if it,
have any non-square matrix, for example, if I have A equal to this 3 cross 1 matrix, 1, 2, 3,
hmm,
okay, and then I have B equal to a 1 cross 3 matrix, let's go with 4, 5, 6. Okay, it's a 1 cross 3 matrix. So we know that AB is going to be some 3 cross 3 matrix. But here you cannot write determinant of AB is equal to determinant of A times determinant of B, because it's not a square matrix, and if it's not a square matrix, its determinant is not defined.
okay.
Right? So
How do we know it is a square matrix in that option?
yes, because it was given to us initially that both A and B belongs to this M n cross n R. So this was the very first fact that we discussed, that it belongs to the space of all the square matrices. So M n cross n R means it is a space containing all the square matrices, all the matrices of order n cross n having the real values. Okay.
Works. What about option two?
Oh, first option we have not done yet. So determinant of AB can be written as determinant of A times determinant of B is equal to 0. Now what's determinant? Determinant is some scalar quantity, right? Some numerical quantity. So it is some numerical quantity times another numerical quantity which is giving you 0. That means what? If I have some A times B equal to 0, this means I can have only three possibilities, that I have A equal to 0 and B not equal to 0. I can have uh, A not equal to 0 and B equal to 0. And then I can have some A equal to 0 and B also equal to 0. So this means in all the three possible cases, at least one of the number must be equal to 0. Intuitive, right? If I'm taking a product of two numbers and the product is coming out to be 0, then one of the numbers should be 0. So
Yes.
same goes here as well, that at least one of the A and B must be 0. So if it says at least one of the matrices A or B is having determinant 0, then this option is correct. Now let's move to the option 2. Okay, any doubts in option 1?
No, sir.
Oh, great.
No.
Moving to the option 2, we have A minus alpha I is equal to 0. So we are given this expression. A is a matrix, again a square matrix. So whenever you see this notation, so you can know that it is a square matrix. And then I is some identity matrix of order n.
Hello.
Sorry.
Continue.
Okay. And then it says if n is even, then the determinant of A is always positive. So what should be our approach?
The
So
property says
A is equals to
minus alpha.
AI,
Okay.
and then we take determinant both side, and A
Okay.
is equals to alpha of alpha I.
Okay. So you said let's write it as A equal to
Yes,
alpha type.
and take determinant both side.
And take determinant on both the sides, because we
Yes,
know that A is a square matrix, so we can take determinant on both the sides, and this entity is also a square matrix because it's
yes.
I times some scalar, so it's
So
alpha times of I. Now,
yes, alpha to the power n, and then determinant of I. So
okay,
determinant of I is 1.
so here comes one more property, that if you have some constant times any matrix, A is a square matrix of order n, then it could be written as k to the power n times determinant of A. So if you want to take any scalar quantity out of the determinant, then you write it as its power n. Okay, whereas n is the order of A. Order of A, given A is a square matrix. Okay, so I can write the thing as A is equal to alpha to the power n times determinant of I. And I know determinant of I is 1. Determinant of identity matrix is 1. So it is alpha
Yes,
to
sir.
the power n only. So it says if n is even, so we know that if n is even, so any constant to the even power is always a positive quantity. Correct?
Yes,
So if n
Yes,
is
yes,
sir.
even, then means alpha to the power n is going to be always positive. Or you can say it as non-negative. Given alpha is real. Okay, so we are not dealing with complex numbers, so we are assuming alpha to be real if it's not given in the question. Yeah, it says alpha is real. Okay, so an is alpha to the power n is going to be non-negative because it can be 0 or it can be greater than 0. So yeah, so second option is also correct.
But
Any doubt?
second option says A should be always positive. Zero is not positive.
And it says determinant of A is always positive. Oh, 0 is not positive. Yeah,
If
that is
alpha
one of
is
the
zero,
case.
then 0 to the power n will be 0.
Yeah, 0 to the power n is 0. So the answer should here should be A is non-negative. But
Yeah,
yeah, we can assume it as positive also. Sorry, 0 also. So 0 also we'll consider in the same option.
yeah. Considered, we can do that.
Yeah. Though the more correct term would have been this
Yeah,
non-negative. But
I also had a confusion in that option.
uh, and do we have any other thing over here where I is identity matrix of order n, A belongs to R, n is even, determinant of A is always positive. Okay, fine. So here the more correct term would have been non-negative in the option. But let's consider 0 as positive for now. Moving to the option 3, it says a matrix with all diagonal entries as 0 will always have determinant 0. So is this option correct?
No.
No, this is not
So
necessary.
let's take a counter example for it. Okay, so if I take a matrix like this, 0, 0, having diagonal entries as 0, but I can take any non-diagonal entry as a non-zero number, then what happens? So if we try to calculate determinant in this case, it comes out to be -1. Okay, so it's a counter example. So we have given a counter example for the statement. This means the statement is not always correct. Okay. Moving on to the fourth option, it says for a square matrix A, if the system of linear equation has a unique solution, then the determinant of A is non-zero. Again, uh, so fourth option says we have Ax equal to 0. Is it 0 or B? Okay, and it has a unique solution. Unique solution, and it says A is a square matrix. A is a square matrix. Then what can you say about the determinant of A? So determinant of A will be non-zero in such cases. Okay, because if in the system Ax equal to 0, A is a square matrix, then unique solution is possible only if the determinant of A is non-zero. That means A inverse exists. Okay, because if you have a system like this, uh, let's say it is Ax equal to B. Okay, and I'm using Cramer's rule here to deduce this. And you need not to go into this detail, but still if you want, that you might have seen that this xi is equal to uh, determinant of axi divided by determinant of A, correct? So this entity could be evaluated only if this determinant of A is a non-zero entity. Okay? So for to evaluate the value for xi and to evaluate a unique value for xi, this determinant of A must be a non-zero entity. So from here also you can reach out to this conclusion. Okay, and we are assuming that A is a square matrix. Only then we can talk about all these things. So option 4 is correct as well. Any doubts in any of the options?
So could you repeat the last option?
Okay, so the last option is if you are given this Ax equal to B as the system, okay, and A is a square matrix. A is a square matrix, then you can remember it as the unique solution is only possible. Unique solution is only possible when determinant of A is not equal to 0. Basically, if A inverse exists. Okay, so you may find multiple terms for the same thing. So if determinant of A not equal to 0, this is also written as non-singular. And A inverse exists, you might find this term for it, invertible.
Okay.
Okay, so moving on to the second question, I hope there are no doubts for the first question. We have
I have a question. How many kinds of solutions are possible? Like there's a unique solution,
Three.
there's infinite, and
Okay, so
No
would
solution.
anyone of you would like to
No
answer?
solution.
Okay, would anyone of you like to take over this question? The question is how many types of solution are possible?
And there is only one type of solution possible, that is unique solution.
No, no,
Because the
not in this
determinant.
No.
case.
For
In general.
system of linear equations, there
You
can
have infinite solutions, no solutions, and unique solutions.
Yeah. So if you have a system like this, Ax equal to B, then your system can be consistent or inconsistent. So when you say consistent, this means that there exists some solution. Okay, so when you say consistent means there exists some solution. So again, you have two possibilities. Either there will be a unique solution or there could be infinitely many solutions. Infinitely many solutions. And then you can say that your system is inconsistent. So that means your system has no solution. Okay, so either there is no solution or there exists a unique solution or infinitely many solutions. Okay, there is no such case of having two solution or three solution. So even if you find something written as that this has two solution, so that would automatically means that it's talking about infinitely many solution, because if you talk about the linear shapes, okay, we are talking about lines, we are talking about planes. Okay, so in linear algebra you can't have something like this, right? If you have a line, so either the second line will cross at a single point, or the second line will overlap, or the second line will not cross. So you get a solution when you find a point of intersection. So you have three possibilities. Either there is a single point of intersection, or both the lines are overlapping with each other, which is a case of infinitely many solution, and or the third possibility is both the lines will never meet. So it's a case of parallel lines, and in that case there is no solution. So we have seen, so this was an example from 2D. So from 2D we have taken this example. Okay, so you can't say that you are intersecting two times, because then this figure is non-linear. Okay, so I hope it clears your doubt. So instead of writing it like this, I'll just write some example over here. So in unique solution, you are having a single unique solution, which is point of intersection. Infinitely many solution, the lines are overlapping. A yes, overlapping lines. And then in case of inconsistent solution, you have parallel lines. Okay, and here you have intersecting lines. Okay, great. Moving to the next question, we again have a theoretical question that consider a system of linear equation Ax equal to B and choose all the options from the following which guarantees a unique solution. Okay, so let's take this question now. So it says it should guarantee a unique solution. So what about option number one? Option number one says A is a square and invertible matrix.
True.
True. Because just now we have seen this option that if you have Ax equal to B and A is a square matrix, and what?
it's
And
also
A is
invertible.
invertible, means determinant of A is not equal to 0. Then you say it's a case of unique solution. But what about option 2? The option 2 says B belongs to the span of column vectors of A. Okay. So if B belongs to the columns, belongs to the span of the column vectors of A, that means what? The solution exists. But again, you can have two conditions. Either the solution is uh, a unique
Unique or
solution,
infinite.
or you are having infinitely many solutions. So again, is there any particular condition given here that would ensure that it is a case of unique solution?
No.
No. So if B belongs to span of columns, we say it's a column space. Okay, so it's denoted by the C of A. Okay, so if B belongs to C of A, then the solution exists. Okay, this basically means you can represent B as the linear combination of the columns of your matrix A. So this means the solution exists, but again, there could be a finite or infinite number of solutions. Not finite or infinite, rather we should write it as it could be a case of unique or infinitely many solutions. So it's just asking about a unique solution. So this option is not correct. Okay. Then it says the column of A are linearly independent. So if the columns of A are linearly independent, that means what? Okay, so that would not see if you might think if columns of A are linearly independent, then A is invertible. Determinant of A is not equal to 0. But you are not given that A is a square matrix. So this can guarantee a unique solution given A is a square matrix. But since A is not a square matrix, uh, this option is incorrect. So we can take a counter example as well. Uh, Columns have to be linearly independent, correct? So what if something like 1 2, and then we are having 2 4? No, not 2 4. Let's have 2 6, and then what? Let's have 3 over here, and let's have 2 over here. So you see, here we are having independent columns, linearly independent columns. Means this column cannot be represented as some linear multiple of this column. So columns are linearly independent, but still if you try to find xy equal to some 1 comma 2, and if you try to solve this equation, it is not guaranteed that you will get a unique solution. Even if I take this example where we have x plus 2y equal to 1, then I have 2x plus 6y equal to 2, and then there is one more equation. I'll write it after some time. So this will give me x plus 3y equal to 1. Okay, so now we need to solve for these two equations. So if so this gives me y equal to 0 and x equal to what? X equal to 1. And now if I try to substitute the value of uh, okay, let's put 4 over here, 1 to 4, because it's a 3 cross 2 matrix and it's a 2 cross 2 matrix. So sorry, not 2 cross 2, it's a 2 cross 1 matrix. So I should get a 3 cross 1 matrix. That's why one additional element 4 over here. And the third equation that I'm getting is 3x plus 2y equal to 4. So if you try to substitute the values of x and y that we evaluated from the first two equations, you see it is not satisfying the equation. That means this system has no solution. So hence we have proved that even though the columns are linearly independent, still we are getting the case of no solution. Why? Because to guarantee a unique solution, the columns must be linearly independent, but the matrix should be square matrix as well. Okay, so this option is incorrect. Any doubts for this
That
question?
means for square matrix, this is valid, not
Yeah.
for rectangular or other size.
No. Because if a square matrix will have linearly independent columns, that it
Yeah,
means
yeah,
you will reach to situation number 1, this option number 1, that the determinant of A will be not 0, will
exactly.
not be equal to 0, and that would mean you will have Ax equal to B. You will have a unique solution for Ax equal to B. Okay. And the fourth option says the system has no independent variables. So what happens if the system has no independent variables? So again, let's take a counter example for it. I want no independent variables, right? So even if I take the same example again, you see that there are no independent variable. I have a pivot over here, then I have a pivot over here. Okay, so two columns, both are pivot columns. So there is no independent variable in this question, but still I'm getting no solution. So the previous example can be used as counter example. Could be used as counter example. Okay, any doubts? So this option is incorrect as well. Any doubts in the second question? You might encounter this one to very theoretical question, and you will have to deduce all these things. You will have to think for the counter examples. Okay. And especially when dealing with these multi-choice questions, just be very careful. Okay, because sometimes it looks that the option is correct, but the option is not correct, and then you lose your marks even for the question options that you have marked as correct. Okay, any doubts for this, or we will move to the next question?
Yeah, we should move.
Okay, here we have let's keep marking the solutions. Mark is correct, remark is correct, mark is correct. uh, this is correct. Now for this one, it says again select all the correct options. Okay, what about option first? Option first says for a vector space V with the dimension n, there is always a subspace for the dimension k where 1 is greater than or equal to k which is less than n. So what about this option? So it says if you have a vector space of dimension n, there is always a subspace of dimension k where k is less than n but is greater than or equal to 1. So is this correct or not?
It's correct.
Correct. Okay, so let's see. First of all, if you have any vector space, then you have two trivial subspaces for it. Okay, so if I have some vector space V, then it will surely have two trivial subspaces. So V is a vector space. Okay, so if I say subspaces of V, so first is 0 is going to be a subspace of it. Okay, so write it as this. Okay, the 0 vector of the same dimension. So it's going to be a subspace of V. Okay, so it's one of your trivial subspace. So it has your dimension equal to 0. And then the subspace having the same dimension. Because every space is a subspace of itself. So it's also one of the theorem that you can keep in your mind. Any subspace, any space is a subspace of itself. Any vector space is a subspace of itself. Okay, so here if we take dimension of V equal to n, then one of the subspaces V itself which also have your dimension equal to n. Okay, so two trivial subspaces are there, one with the dimension 0 and one with the dimension same as the subspace. Okay, but it says we are not considering this case of dimension n, and we are not even considering this case of dimension 0. So is it guaranteed that we will have other subspaces as well? So yeah, this is also true. Even if I take any example like this, So it's a two-dimensional subspace in R3. So how can I represent a two-dimensional subspace in R3? So let's suppose this is my R3 and this is some plane that passes through origin. Passes through origin.
Yeah, then
Oh,
it's a 2D subspace.
okay, so all these are non-trivial subspaces. Non-trivial subspaces example.
Trivial and non-trivial subspace example.
A trivial means you'll always find these two subspaces. That's why we call it trivial. That whatever happens, these two cases will be there. If
Okay.
you're talking about a zero space, so also it satisfies both the condition because uh, zero is a subspace of itself, and then there exists a zero, which is a subspace of itself again. Even if you talk about a line, so if there is a, I talk about any vector space in one dimension, let's talk about R. Okay, R1. So R1 also contains the zero as a subspace, and R also has R itself as the subspace. Okay, if I talk about R2, then I have zero, I have R2 itself, so both are the trivial ones, and then I have some non-trivial ones also, like any line that passes through the origin is also a subspace of R2. Okay, so what are the conditions that we require for something to be a subspace? That it should uh, first include or inherit the zero vector from its parent space, and then the second case is it should be closed under the vector addition and vector multiplication that we defined in our parent space.
Yeah. Okay.
Okay, yeah. So coming back to this, we have what was it? Yes. So example of non-trivial subspaces, right? So if I take, let's say V is in R2, let's say, and not just R2, let's say V is in R3. Let's say uh, V is some plane in R3 that passes through origin. Passes through origin. Okay, so it's like I have an origin over here, and then I have this plane that passes through origin, and I'm calling this as my vector space. This plane as my vector space. So any line on this plane that also passes through origin is a subspace of V. Correct. So for this example, any line lying on V that also passes through origin is a subspace of V. Correct. So if I call it S, if I call this space as S, where was it? Any line passing through, any line lying on V that also passes through origin, I'm calling it my S. I'm calling it as S. So you see the dimension of V that I assumed was 2 in this case because it's a plane. Okay. Though it is in R3, but still it's a plane. So that's why the dimension is 2. And the subspace that I'm talking about S is a line. So the dimension of S here is 1. So hence we have shown that there exists some subspace having the dimension less than 2 and greater than or equal to 1. Okay, so a better way to write it would be so that even if you check it later, 1 greater than or equal to dimension of S. So we have shown this for this vector space, and similarly you can show this for any vector space. That's why the option number 1 is correct. Okay, any doubts on this?
So in that plane, actually, there is a line that is a minimum one dimension.
Minimum one dimension means, see, any line you sketch, it will have a dimension 1 only. Okay, even
Yeah.
if the line lies in R3, still it is having a single dimension.
Yeah, correct.
So we have not taken any bigger space so that it is easier for us to visualize this, because in higher dimensions we can't visualize it. That's why we have taken V as uh, some subspace in R3.
Okay.
Okay. Then it says let S be a set of k vectors in Rn. Then span of S has dimension less than or equal to k. Okay. So this time it says uh, S is a set having k vectors. Okay. So S is a set of having k vectors. So I'm writing it as cardinality of S is k. Cardinality means the number of elements in a set. Okay. So the cardinality of S is k. Then what? It says the span of S. Okay, if I talk about the span of S means all the possible, the space spanned by all the possible linear combinations of the vectors of S. So it says the span of S can have the dimension less than or equal to k. So is it correct or not? This
Correct.
is the option, right? Yeah. So this option is correct. Why? Because see, what are the possibilities? First possibility is if all k vectors are independent. Okay, all k vectors are independent. If all k are independent, then in that case, see, dimension is the number of independent vectors that I am having in my span. Okay, this is one of the way to find the dimension. If all k are independent, because dimension is basically the cardinality of your basis. Okay, so if I take any spanning set and I take only the elements which are independent, I take only the vectors which are independent, that would give me the basis. And then I can count the number of vectors in that basis. That will give me the dimension. So basically, dimension is the number of independent vectors in any given set. Okay, so if all k are independent, in that case, I will get dimension of S equal to k. Okay, and what is the second possibility? So second possibility, if there exists any k, so this is a symbol of there exists. Okay, so if there exists any k, okay, there exists any vector in S which is dependent, which is dependent, or basically you can say that S is a dependent set. So in that case, the dimension of S is going to be not less than or equal to less than k. Why? Because if even one single vector is could be represented as linear combination of other vectors, then it means that vector is would not be counted as independent. Okay, so if there is one dependent vector, then the dimension is going to be k minus 1. If there are two dependent vectors, then the dimension is going to be k minus 2. So in any case, the dimension would be less than k if there exists any dependent vector. Okay, so if I consider all these cases, so I can say the dimension is always going to be less than or equal to k. So if all are independent, then it is equal to k. If there exists any vector which is not independent, which is dependent on other vectors, then the dimension would be less than k. Any doubts on this? Questions? Any questions? Yes, no?
No.
Okay, great. How many people do we have here? Okay. Then so what we said, the first option is correct, the second option is correct. Let's move to the third option. The third option says let S be a subset of vector space V of dimension n, then S can have a minimum of n linearly independent vectors. So again, let's try to parse this option. It says S is a subset of vector space V of dimension n. Okay, so V is a vector space and S is a subset of V. Okay, so just see here, it does not say that S is a subspace of V. Okay, it's not a subspace, it's just a subset. Okay, then it means it contains some of the vectors from this vector space V. Then S can have a maximum of n linearly independent vectors. So it says that the dimension of V is given as n. Dimension of V is given as n. So it says S can have at max n independent vectors. So is it true or not? Is it true or not? Okay, so I'll show one example and then you say. Okay, so example is, let's say we are going with R3, R2 first, let's say. So I'm taking S from R2, any set from R2. Okay, so I'm taking random vectors 1, 1, 1, 0, 0, 1, 3, 4. So you see S is a dependent set. Okay, it has dependent vectors because 1, 1 can be represented by 1, 0 and 0, 1. So one by one, let's start to eliminate the vectors. So even if I remove 3, 4, this set is still a dependent set. Okay, if I remove 1, 1, now it's not a dependent set because 1, 0 cannot be used to represent 0, 1, and 0, 1 cannot be used to represent 1, 0. See, 3, 4 were 3, 4 was dependent. Why? Because I can write it as some 3 times of 1, 0 plus 4 times of 0, 1. So it was a dependent set, I removed it. Then what? 1, 1 could be represented as 1, 0 plus 0, 1. So again, it is dependent on 1, 0 and 0, 1, so I removed it as well. But now 1, 0 cannot be represented by some linear combination of just 0, 1. And 0, 1 cannot be represented by some linear combination of 1, 0. Okay, so now these two vectors are independent. Okay, so what I saw was, if I take any set, so at max I can have only two independent vectors. Okay, same goes with R3. If I talk about R3, I can have, if I take any set from R3, okay, so if S is some subset of R3, then it can have at max 3 independent vectors. Max 3 independent vectors. Okay, same goes for R4. If I have R4, I can have at max 4 independent vectors. Okay, why only 3 independent vectors? Because let's say I have taken this 1, 0, 1, 0, 0, and then I have taken 0, 1, 0, and then I have taken uh, 0, 0, 1. So any x, y, z, that is any other vector of this R3 can be represented by the linear combination of these three vectors. How? I can just write it as, I have some x times of 1, 0, 0, and then I have some y times of 0, 1, 0, and then I have some z times of 0, 0, 1. Okay, so if I have these three independent vectors, rest all the other vectors can be written as the linear combination of these three. So I cannot have more independent vectors in R3. Okay. So this option is correct. So if you are having some Rn, so in general, if there is a set S which is a subset of Rn, then at max it can have n independent vectors. Okay, and even if we not talk about these spaces, and if we try to write something as like this, that S is a subset of V, uh, where the dimension of V is equal to n, then here also at max S can have n independent vectors. Okay, so any questions on this? Second option is also, third option was it, right? It's also correct. Okay, any questions? Yes, no?
Sir, it's not about this question. I have this doubt with this term itself, maximal independent set.
Okay.
They've confused me a lot.
Yeah, let's see. Let's move to the next page. So you might have seen this with the bases. Whenever we talk about bases, we write bases can be said as maximally independent set and it can also be termed as second, right? Minimally spanning set. Okay, both are true about the basis. So let's first talk about the first one that says maximally independent set. Okay, so I'm taking any set in R2. Any set that contains any set of V that belongs to R2. Okay, any set of vectors V that belongs to R2. So I'll start putting elements here. Okay, so this S. So initially I'm just going with 1 comma 1. So because it's a single element, so it's independent. Set is independent, correct? Because it only contains one element, one vector. Let's add another vector to it. Okay, so another vector is, let's say in 1 comma 1 I try to add what it could be, any other vector, just name any vector. Let's take 3 comma 4. Okay, I added 3 comma 4 over here. Now you see S is still independent. S is still independent. Why? Because 3 comma 4 cannot be represented as some k times of 1 comma 1. Correct? Yes, no?
Oh, yes.
Okay. Now let's try to add one more vector to it. Any other vector? 1 comma 1, 3 comma 4, and let's write it as any number, 5 comma 6. We'll see whatever it will be. Now the question is it still independent or not? So what we saw was, if you have uh, some vector which is in the dimension of n, then your S can contain maximum of n independent vectors. Okay, so it cannot have more than 2 independent vectors. How you are so sure about it? So even if you see that 5 comma 6 can be we are claiming that if I have 5 comma 6, so it could be represented as some linear combination of 1 comma 1 and 3 comma 4. This is our claim. Okay, so again you need to solve for this system. So this will give you two equation, two variable. Okay, this will give you two equation, two variable that you need to solve. So what we are saying is let's write it as uh, either you can write it an ax equal to b form, or even if you just try to do simple math over here, a plus 3b is equal to 5, whereas a plus 4b is equal to 6, then you will get a unique solution out of it. Okay, now
For now, is it unique or is it always that it is unique?
yeah. So the claim is, if I already have got two independent vectors,
The third will be automatically independent.
so third will automatically be dependent. If I'm talking
Dependent,
about R2, yeah,
not independent.
yeah. If I have already got two independent, then if I add third, so it will be dependent.
Okay.
Okay. So what about this case? I'm just taking so that there is no confusion left. If I start with S as some 1 comma 1, so it is independent now, and then I go with and then I try to add some 2 comma 2. So now you can't say that if you add any third vector, it would be it would be dependent. Why? Because 2 comma 2 is still dependent on 1 comma 1. So here only it became dependent. It became dependent now. So it can't be my basis. I can't use it as my basis because it is dependent. Okay, so
But
a
still, 1
basis,
comma 1 is independent, no?
yeah, this guy is independent.
Okay.
And now I tried to add something else and it became dependent. So the claim is at max I can add only at max I can add any two independent vectors.
Yeah.
Okay, so here it was independent. Then I added something, it is still independent, but then it became dependent.
So the whole yes, actually, we should say as independent. Yes, sorry, dependent. If it is any linear combinations.
Sorry, could you repeat, please?
If any dependent games means the entire the S, we should call it as dependent.
In 1 comma 1, 3 comma 4, and 5 comma 6, S is called a dependent.
Dependent.
S will be called the dependent set.
Okay.
Okay.
And
Okay.
not necessarily every time we add one element, one set of numbers, it will become dependent, right? It is not necessary, right?
Yeah. So
Sometimes it may still remain to be independent set.
yeah. So the claim here is at max you can have
3 sets of numbers.
n independent variables. Sorry, not variables, vectors inside your set. Okay, where n is the uh, dimension.
And adding anything beyond that will lead into dependent.
Yeah.
Yes.
Okay.
Okay. And second comes minimally spanning. Okay. So minimally spanning means
Hello,
it
sir.
yeah.
Depended how we are guessing, sir.
Dependent means if one of the vector could be represented as the linear combination of other vectors, then we say it is dependent. Okay. So 5 comma 6 could be represented as linear combination of 1 comma 1 and 3 comma 4. That means we are saying if you try to solve this equation, okay, this system of linear equation, you will get some solution. Means it will not result in no solution.
Hmm. If solution exists means then it is dependent.
Yeah, it is dependent. Okay, so I'll tell you one way to check whether a set is dependent or not, but let's just complete the second point first and then we'll go there. Minimally spanning set. So minimally spanning set is, first we need to know about what is a spanning set. So spanning set is a set that can span the entire space that we are talking about. So if I talk about R2, okay, so the entire R2 can be spanned by a set having two independent vectors in R2. Okay, so the entire R2 can be spanned by a set can be spanned by a set having two independent vectors in R2. Uh, and can I represent it mathematically as well? Yes. So any R2 will have this point x comma y, right? So I can say that any x comma y could be represented as some x times of 1 comma 0 plus y times of 0 comma 1. So you see, if I talk about these two vectors 1 comma 0 and 0 comma 1, they can span the entire R2 for me. Okay, so I'm calling it the spanning set for R2.
But if you then add 1 comma 1, that will be linear combination of the first two.
Yeah, just a second. So spanning set of R2. Okay, then we are making one more claim that any superset of a spanning set is also a spanning set. Any superset of a
Superset, what is that?
superset means if you add any other element to it, so it will become bigger, right? So it's a
Oh,
superset.
yeah.
So any superset
Any
of a
dependent.
spanning set is also a what? Is also a spanning set. So here if I
Actually,
say, yeah, please go on.
actually, a superset is like making that spanning set as dependent. Can I say that?
You are saying if I make a superset, then it will become dependent. Yeah, correct.
Ah,
So
okay, okay.
we'll just see all the things, but let's first cover this point. It says any superset of a spanning set is also a spanning set. That means what? Even if I add any vector to it, okay, one or two or any vectors of my choice, okay, any number of vectors, it will still remain a spanning set because I can still represent x comma y as linear combinations of these vectors. Okay, so I'll just use a very simple way of doing it. I'll just say some 0 times of 1 comma 1. Okay, similarly, if you add more elements to this set, more vectors to this set, still I can write 0 times of that. That would still give me any x comma y. Okay, so it still remains a spanning set. So if I can say that any superset of a spanning set is also a spanning set, so I can have multiple spanning sets for R2. Okay, this suggests that I can have multiple spanning sets of not just R2, any Rn. Okay, spanning set for any vector space. Okay, and this also gives you one thing, that spanning set is not unique.
Because we can add n number of
Yeah,
linear combinations.
yeah, you can add n number of linear combination. That's why the spanning set is not unique. For example, if I take R2, so I can have multiple spanning sets. Like I can have 1 comma 0, then I have 0 comma 1, then I have 5 comma 4, then I have 6 comma 3, then I have okay, let's stop here. Okay, so in this scenario I can talk about minimally spanning set, like which set is the minimum such that it can cover the entire space. Okay,
The
so
first
let's
two. Yeah.
try to remove elements from it. Let's remove 6 comma 3. So I'll be left with 1 comma 0, 0 comma 1, 5 comma 4. Okay, still it is a spanning set, but can I remove more elements? Let's try removing 5 comma 4. Okay, it's still a spanning set. But let's try to remove 0 comma 1. So we are only left with 1 comma 0. So we cannot remove more elements now. Okay, so we have reached to the minimum limit such that it remains a spanning set. Okay, comma 0 is the minimum set such that it's still a spanning set. Is still a spanning set. Okay, if I try to remove more elements from it, it will no longer be a spanning set, because if you just have 1 comma 0, so you cannot cover all the points in R2. Okay, because if you have just 1 comma 0, that means you are having just a single vector. Okay, just a single vector can cover a line, but it cannot cover a plane. To cover a plane, you need two vectors which are not linear. Make sense? If you want to cover a plane, then you want two vectors. And now you take linear combination of these two vectors, and then you can cover any point in the plane.
Actually, apart from this 1 comma 0 0 comma 1, I can we can just directly 4 comma 5 comma 4 a single vector can span this minimum
No, a
set
single
of.
vector cannot span this. So let's say uh, this is my R2, correct? So this is my R2. Let's change the color. This is my R2. Okay, so I want to cover this entire plane. Okay, so you say if I just take 5 comma 4, so 5 comma 4 I assume would be somewhere here. So this vector is my 5 comma 4. So what can it span? So it can span, the alone vectors can span the entire line on its own.
Okay.
But what about the points which are not in this line? Okay, so for that you need another vector which is not linear to this 5 comma 4. So if you take any other vector, let's suppose it lies here. Okay, then you take any combination of it. You know, right? You can scale it and then shorten it. If they are not in a single line, so the
Yeah.
combination of this vector can complete the
Span
entire
this. But
right.
still 5 comma 4 6 comma 3 we can write it. Can
Yeah,
we write?
yeah.
Yeah.
So we were getting to this point only. So we say now we cannot shorten it more. So this is basis. So basis is a spanning set such that you cannot increase elements to it, because if you increase element in the basis, then it will no longer be linearly independent. Correct? That's why it's maximally independent, and you can't even decrease the number of vectors, because if you decrease the number of vectors, it's a minimally spanning set, so you can't go like uh, you can't remove more elements from it. Okay, because then it will no longer be a spanning set, and if you try to add more elements to it, it will no longer be linearly independent. Okay, so we say basis is a linearly independent spanning set. Linearly independent spanning set. Okay, so is this also fine? Okay, so like we talked about spanning set, that the spanning set is not unique. The same thing can be talked about basis also, that basis is also not unique. Is also not unique. Why? Because see, I talked about a basis of R2, correct? So one of the bases of R2 was 1 comma 0 and 0 comma 1. But as we seen here in this example, any other combination also which is non-linear will be able to span the entire R2. So even if I take 5 comma 4 and 6 comma 7, okay, that would be able to span the entire R2. Okay, and similarly, I can take any two or any two independent vectors from R2. vectors from R2. Okay, that would still be a basis of R2. So basis is also not unique. So why we emphasize so much on basic? Because though the basis is not unique, but the uniqueness, but there is one more thing, one good thing in basis that we lack in spanning set is, see, here you can have spanning set of any length because we are allowed to add more elements to it, correct? But what happens in a basis is the number of elements of the basis will remain unique, will remain the same. Though you can have different sets being the basis, but all the sets which are basic will have the same cardinality. Cardinality same means the number of vectors that they contain is going to be same. So even though I can take any two independent vectors from R2, so I cannot put the restriction on which vectors I am taking, but I have one restriction that both
The cardinality is 2.
can be two only. Okay, so from the base, on the basis of basis, we define something called dimension, because we have said that the cardinality of basis is constant. Okay, the cardinality of basis uh, is same. Okay, or yeah, or we can say is constant. And is, so that's why we use a term for it called dimension. This termed as dimension of vector space. So if you want to find the dimension, if you want to find the cardinality of any set, what you do is you first find the basis, and if you want to find the dimension of any vector space, you first find the basis and then you check the cardinality of the basis. So for example, here the cardinality of the set is 2, hence the dimension of R2 is 2. So that's a reverse approach.
Yeah.
Okay, so we were going to talk about one point, which was how to calculate basis. How to find basis of a spanning set. A spanning set. So oftentimes you'll encounter a situation like this. For example, S is given as some set. Okay, let's take it as 1, 4, 5 and 1, 7, 8. Yeah, I should take one example so that I'll be able to show what's happening here. Just give me a second. So I'll have some written examples over here so that I can pick any example. Where is it? Where is it? Where is it? Okay, great. So let's take one example where we have this as 1, 2, 0, and then we have 0 1 1, and then we have 1 3 1. Okay, so you may encounter the question in different ways. It may tell you that okay, V is some space which is a span of S, and then you find the dimension of V. So how will you find it? So S is some spanning set, so you first need to find the basis of S. Okay, so how will you find the basis of S? So you need to check which of the vector is linearly dependent. Okay, so uh, a good way of doing it is you put all the vectors as the rows of a matrix. Okay, so I'm putting it as 1 2 0 0 1 1 and 1 3 1. So all these are rows of a matrix. Okay, and then I perform the row operations, okay, row reductions basically.
I can write it as a column vector also, no?
No. Why? Because see, the aim is we want to check which row will become 0. Okay, we will because we are only going to do the row operations, hence we are taking them as rows. Okay,
Sometimes the vectors are taking most of the time is the column.
yeah, so the purpose is different in that case, na? So purpose is in those cases we try to solve the linear equation. We are not trying to solve the linear equation because for linear equation we are interested in the how to say it. There the vectors represent the coefficients of
Hmm.
the variables.
Yeah.
Okay, but here we are just checking whether the vectors that we have, they are dependent or independent with each other.
So actually, each year 1 2 0 means x, y, z. Three vectors are here, correct?
1 to 0 means this is one vector. Okay, so each row represents one vector. So this is one vector, this is another vector, and this is third vector. Okay, so the purpose is, see, I'll tell you why why we are taking them as rows. Because if I say 1 3 1 can be represented as 1 2 0 plus 0 1 1. So this was easy to spot here. But if you have, let's suppose, multiple vectors, it's not very easy to spot. Correct. So rather what we can do is, if we represent them as rows and we perform the row operations, that you subtract it, subtract it. So in a way you are just performing these operations only. In a way you are just trying to find out that linear combination of which two rows can represent the third row. Okay, so we are trying to find which row can be represented as the linear combination of other rows. Okay, so I'll tell you the purpose. Which row could be represented as a linear combination of other rows. Combination of other rows. So basically we want to perform row reductions here. So that's why now see, this is the usual thing that we do. Okay, for the row reductions, the purpose is to find which row could be represented as a linear combination of other rows. And what was our question? Our question was which vector could be represented as linear combination of other vectors. Okay, so you see, the purpose of row reduction is to check which row could be represented as linear combination of other rows. And here what we want to do is which vector could be represented as linear combination of other vectors. So don't you think we should put the vectors as rows in this case? So that's why when we want to find a basis corresponding to a spanning set, we should put them as rows. And now we perform the row reductions. So here one of the row reduction that we are going to perform is R3 minus R1 minus R2 minus R1. Okay, that is from R3 you are subtracting both R2 and R1. That will make this row 0. And now you see this guy is an REF form. So the non-zero rows of the REF, non-zero rows of REF represents the non-zero row of the REF represents the independent rows. Presents the independent rows. And what we wanted, we are using vectors as rows. That means non-zero rows are representing our independent vectors. So since we have used vectors as rows, thus non-zero rows represents uh, independent vectors. Independent vectors. And what do we want? We want independent vectors because independent vectors will make the basis for us. The basis in this case is what was it? 1 comma 2 comma 0 and 0 comma 1 comma 1. So if you now want to find the dimension of V, so dimension of V is the cardinality of B, which is 2. So what can you say about V? So we initially saw that the points that we have, the points are in R2, R3, sorry, because it has X component, Y component, Z component, but the dimension of V is 2. So what can I say about V? So V is some plane in R3. It's some plane in R3. Why we are calling it a plane in R3? Because it has a dimension 2. So it has a dimension 2 means it is a plane. Okay, but it is in R3. Why? Because see, every vector has 3 components. That is why it's in R3. But since it is vector space, it must pass through origin. So some plane in R3 that passes through origin. Passes through origin. So basically, if you want to visualize it, you can visualize it like this. There is some space in R3, some plane in R3. That could be your V. Okay, once you know the basis, all these things you can derive out of it. Okay, any doubts here? Moving back to our original question, the fourth option says a non-finite empty set of vectors from a vector space can never be a subspace. Sorry, a finite non-empty set of vectors. So it says a finite set cannot be a subspace. So we have seen a line is a line can be a subspace of plane, but again a line has infinitely many vectors. Same goes with a plane. Plane also has infinitely many vectors. So you may think that okay, there cannot be any subspace that contains only a finite number of vectors, but no, there is a subspace that contains only finite number of vectors, which is your 0. Okay, so if I talk about this 0 vector, so it is a subspace just containing 0 vector, subspace having finite vectors because it only has a single vector, which is your 0 vector. Okay, so there exists so we are saying that there exists a finite non-empty what was it, set, where were we, non-empty set that can form a subspace. So option number 4 is incorrect. Okay, so any questions? Hey, this is incorrect. Okay, any questions so far? You might find it little overwhelming, but trust me, it's just you derive from the things. You need not to think a lot about everything. Okay. Is it necessary that a plane is passing through origin? No, it is not necessary for a plane to pass through origin, but if we say V is a subspace, so a subspace must pass through origin. Okay, so if the plane is representing a subspace, then it must pass through the origin. Okay, great. The fifth question is something, then A transpose is a matrix, then it says find the value of alpha and then find the value of beta. Okay, now we are done with the theoretical questions. I believe all the questions that we'll get from now will be calculation based. Okay, so we can quickly finish all of it. And just let me tell you one thing about maths 1, maths 2, sorry. So in maths 2, the first quiz that you will be having uh, is the best chance for you to score. Okay, so the first quiz and the ET. Okay, because the quiz 2 may contain some of the contents that you may find a bit difficult. Just focus on quiz 1, please. Yeah. So it says A times A transpose is this. So let's find A times A transpose. So A is minus 2 alpha, beta, and 2. And then A transpose is transpose of this. So transpose means you interchange rows with columns. So this is my first row, I'll write it as a column. So minus 2 alpha. And this is my second row, I'll write it as second column, beta 2. That will give me 4 plus alpha square plus 4. I'm assuming that we all are good with matrix multiplication. And then comes 2 alpha minus 2 beta. And then we have minus 2 beta, then 2 alpha. So again 2 alpha minus 2 beta. And then we have beta square plus 4. So it looks very symmetrical, right? So now we will compare this matrix with this matrix over here. So what we can deduce is that 2 times of alpha minus beta is equal to 8. That is our first equation. The second equation says alpha square plus 4 is equal to 8. That is our second equation. And third says beta square plus 4 is equal to 8. So this is our third equation. Okay. So now based on this, if we solve these two problems, we get alpha is equal to plus minus 2 and beta is equal to plus minus 2 again. Okay, so we'll be testing these two values because simultaneously it should satisfy all three equations. So we have alpha minus beta equal to 4. Now let's try with the alpha equal to 2, beta equal to 2, alpha equal to 2, beta equal to minus 2, alpha equal to minus 2, beta equal to 2, and then alpha equal to minus 2, beta equal to minus 2. So we will have to test all the possible combinations for alpha and beta. So you see this gives what? 2 minus 2, 0. So it gives 0 equal to 4, which is incorrect. So on the left hand side here, this time we will get 2 minus minus 2. So this is correct. Then it says minus 2 and then minus 2 again. So this is minus 4 equal to 4. This is incorrect as well. And if we put a minus 2 here and then minus 2 again. So minus 2 minus of minus 2. So that is minus 2 plus 2, which is 0. So it again gives you 0 equal to 4, which is incorrect. Okay, so the answer is alpha is equal to 2 and beta is equal to minus 2. Okay, so here we write alpha equal to 2 and beta equal to minus 2. Any doubts on this?
Can you please show the calculation?
Yeah.
Okay,
So
thank
is it
you.
done? Yeah. Moving to the next question, we have, it says A is a 5 cross 5 matrix such that A transpose A transpose is equal to minus A, then determinant of A. Oh, sorry. Insert page after. Here we can have one result, which is, I'm writing a result over here and we'll write a proof for it. Okay, the same proof can be used for this question. So we had some question over here, let's clarify. So the result is, if A is a skew symmetric matrix of odd order, skew symmetric matrix of odd order, then determinant of A is equal to 0. So let's prove it. Okay, so first it says skew symmetric. Okay, so skew symmetric means it's a square matrix first. Okay, and it follows the property A transpose is equal to minus of A. Skew symmetric means A transpose is just equal to minus of the matrix. So how to find determinant in this case? Let's take determinant on both sides. So it will be determinant of A transpose is equal to determinant of minus of A. Okay. So one thing is that determinant of A is equal to determinant of A transpose is equal to determinant of A. Okay. So on the left hand side I have determinant of A, and on the right hand side I have, if I try to take minus symbol out, it will be minus 1 to the power some n times determinant of A. Now you have two possibilities. Okay, one possibility is n is odd. If n is odd, what you can write? You can write determinant of A is equal to minus 1 to the power odd is minus 1 again times determinant of A. So now you take this to left hand side, or let's write one more step, it is equal to minus of this. So you take this to left hand side, that gives you 2 times of determinant of A equal to 0, and that gives you determinant of A equal to 0. So see, we saw that if it is a skew symmetric matrix of odd order, then the determinant of A is equal to 0. But if n is even, so it's inconclusive, you can't make any conclusion out of it. Why we say so? Because see, if it is even, then determinant of minus 1 to the power even is plus 1. So that gives you determinant of A equal to determinant of A. You can't conclude anything out of it. Right? So that's why we are saying that it's inconclusive. It's true. Okay, any doubts? So for this question, the question was, A is a 5 cross 5 matrix and A transpose is minus A. So we can use the same result over here and we can say determinant of A is equal to 0 since 5 is odd. Any questions?
Could you please repeat that?
Oh, this part.
Yeah, just a quick.
Okay, so see, we are saying we are having a skew symmetric matrix. That means a matrix that satisfies A transpose is equal to minus of A. So let's take determinant on both sides. It becomes determinant of A transpose is equal to determinant of minus of A. So determinant of A transpose is equal to determinant of A itself, property. And then if we try to take minus 1 out of it, because it's a constant quantity, so we
Yeah.
will have to put its power as n, then times determinant of A. So now if n is odd, so minus 1 to the power n will become minus 1 only, and then you can write it as determinant of A is equal to minus of determinant of A. You take this entity to left hand side, it becomes 2 times of determinant of A equal to 0, and if you divide both sides by 2, you get determinant of A equal to 0.
Okay. That's actually skew symmetric matrix. Even power, it is always it is 0. The determinant.
No, for odd power, its determinant is always 0.
Okay,
For
sorry.
even
Odd
power, you
power.
can't make any conclusion.
Okay.
Okay. Okay, this is not the question that we wanted. We were here. So the next question here is let 4, we have done 5 with 6, right? It says A is a 2 cross 2 matrix such that determinant of A is equal to 2. If B is a matrix obtained from A by swapping the first row and the second row and then multiplying the second row by -2, then determinant of B will be what? See, we have seen this, right? 3 operations with determinant. If you swap some rows and columns, so swapping means you need to multiply the value of determinant by -1. Correct? Then if you say you are uh, multiplying any constant to a row, okay? So multiplying any constant or scalar to any row slash column. That means you will have to multiply the value of determinant by the same entity. By any scalar, let's call the scalar lambda. So you will have to multiply the determinant of A by the same scalar. So now you see what are the 2 operations that we are doing over here. First, we are saying that determinant of A is equal to 2. Okay, how B is obtained? So you say you interchange the rows of B. First, you interchange the rows of A. If you want B, you swap first and second row. That means first you are going to multiply the determinant of A with -1, and then you say after that you are multiplying the second row. So you multiply a row with a constant. That means what? You will have to multiply the value with the same constant times -2. So what was the value of determinant of A? It was 2 initially, correct? So 2 times of -1 times -2 becomes 2 again, and it's 4. Any questions on this? So you would have done in your 12th class. Any doubts on this question? Yes, no? If there are no doubts, we can move to the next question. So the next question here says find the number of independent variables. So how you find the number of independents? You first change your matrix into the RREF or REF form. Okay, change your matrix in REF form and then mark the pivots. And then what? The pivot columns. So the variable corresponding to the pivot columns are your dependent variables. Okay, variable corresponding to pivot columns are your dependent variables. Whereas the variables corresponding to the non-pivot columns are your independent variables. So first let's mark the pivots. Here we have one pivot, here we have another pivot, here we have our third pivot. It's already in REF form. Okay, so means if I'm calling this as my x1, this as my x2, this as my x3, this as x4. So this means the variable corresponding to first column is x1, second column x2, third column x3, fourth column x4. So from here I can derive that x1 x3, x4 are dependent. Why? Because they're having pivots. Okay. Whereas x2 is not having any pivot, so x2 is independent. Okay. So it says number of independent variables, so the answer is 1. There is only one independent variable. Any questions?
It is for only ax equal to b or ax equal to 0.
No. Independent. When you talk about the dependent and independent variables, you just look at the a. Okay. Right hand side does
Okay.
not matter.
Some question it is confusing actually. Ax equal to 0, ax equal to b. Solutions different. So
Yeah. So we'll just cover that point also. Okay. Homogeneous and
okay.
non-homogeneous. Let's first finish the paper.
Okay.
Find the dimension of subspaces in the given questions. Okay. So from here we need to uh, find dimensions. Okay. So the question will be to find dimensions of subspaces. So again, we'll use the same strategy to find the basis first. So first one is here. W1 is this. You need to find a basis for W1. So let's call it the first one. It says W1 is equal to x belongs to Rn such that Ax equal to 0 where A is an invertible matrix. Okay, so we anyway came to Ax equal to 0, right? So if you have Ax equal to 0, right? In Ax equal to 0, there are only two possible cases. Either there is a unique solution that we call our trivial solution, which is your x equal to the 0 vector. Okay, and the second one is infinitely many solution. Many solution. There are only two cases. So that's why we say the homogeneous system is always consistent. Because see, in any case you see you have any pair of linear equation. I'm saying a1x plus b1y equal to 0 and a2x plus b2y equal to 0. So if you want to satisfy this, you always have one solution which will always be true. Put x equal to 0, y equal to 0. This solution will always be true. Correct? This solution will always satisfy both the equations. So homogeneous solution always consistent.
Okay.
Always consistent. Okay, again, we say Ax equal to 0. This is a general case, okay, with A as a square matrix. So what if A is a square matrix? Then what can you say about it? So again, you have two cases, same two cases. Okay, X is a 0 vector or infinitely many solution. This is unique and this is infinitely many solution. Really many solution, but you have more information this time. So you say if determinant of A is not equal to 0, then you get this. If determinant of A is not equal to 0, then you get this case. But if determinant of A is equal to 0, then it's a case of infinitely many solutions. So coming back to W1, W1 says all the possible values of X, all the possible solutions of this system. So if A is invertible, there is only one solution, that is 0 vector. Okay. If A is invertible, then Ax equal to 0 has a unique solution. And that solution also we know. Solution is x equal to 0 vector. Okay, so W1 contains only one single element. Okay, so how will you find the dimension? So if it contains one single element, then the dimension is 0. If it contains one zero vector only, the dimension is 0. Okay, because the span of 0 vector is always a point. Okay, so the space spanned by the 0 vector is going to be point only. Okay. If it would have been any other vector, then you say the space spanned by the vector is a line, and then it would have dimension 1. Okay, so if your basis contains a single vector and the vector is the 0 vector, then you say dimension is 0, because 0 vector can only span a single point. But if you say it's a non-zero vector, then if it is a non-zero vector, it can span a line. Correct? So in that case, the dimension will be 1. So this is something you need to keep in your mind.
So Ax equal to 0, that is only two option, unique and infinitely many. Like that's it.
Yeah. You don't have the option of no solution. So here the answer is 0. Then you say span of this. So again, see, here a spanning set is given to you. So again, we did something similar, right? What was it? To find the basis and then to calculate the vectors in the basis. So to find the basis, first arrange them as the rows 4, 1, 2, and then 2, 3, 0. And then let's perform some row operations. So if I say that you do something like this, that in R2 you subtract 2 times of R1 and then R2 also. Okay, so what you will get 0, 0, 0 here. Just try doing it. 2, 3, 0, yeah, looks fine. Because it's 4 minus 2 minus 2, 0. And 1 minus minus 2. That is 1 plus 2, then minus 3. 1 plus 2 minus 3, 0 again. And then 2 minus 2 minus 0. So 0 also. So see, this is a 0 row. So you eliminate the 0 row and you only take the non-zero rows. Okay, so the basis is 1 minus 1, 1. And then 2, 3, 0. These are independent. Okay, you can't represent 2, 3, 0 as some linear combination of this. So the dimension of W2 is going to be 2 because the basis contains 2 elements. Okay, any questions on this?
The previous question, Rn equal to 0. Yeah. That is actually how it is. Rn equal to 0.
Where is it? Rn equal to 0. We say dimension
Yeah,
of
that
W1 is equal to 0.
that is actually W1 equal to 0. What is that actually? Couldn't
This
relate actually.
Okay. See, we have the first we tried to find the basis for W1. So
Yeah.
the basis we got as a single point. Okay. So the single point, which is a
That
0,
dimension is 0.
has the dimension 0. Means the space spanned by this will have dimension 0. Okay, because 0 vector is just a point. Okay, even if you want to see mathematically, 0 vector will look something like this: 0, comma 0, comma 0. Okay, this is your 0 vector. So what is the space span of 0 vector? So if I write the span of 0 vector, it would be some k times of 0, comma 0, comma 0. I can vary the value of k, but doesn't matter which value for k I choose, it will still remain 0, comma 0, comma 0.
Okay.
So that means the span is just a point.
Okay. There is no, I'm not given any zero vector over there. X belongs to Rn.
Uh,
The
this
question.
the
Yeah.
question says x belongs to R of n such that ax equal to 0 where a is invertible. So it says x is a solution of this homogeneous system such that a is invertible. So you try to find the solution of this system where a is invertible. And then you will
Okay.
find that if a is invertible, then this system has only a single solution, which is x equal to 0
Zero.
vector.
Okay. Got it. Yeah.
And then moving to the next question, we have W3 is a set of all 2 cross 2 symmetric matrices. Okay, so the idea of basis is not going to change. Okay, we will still try to find the basis because anytime we want to find the dimension, we try to look for the basis. W3 is the set of 2 cross 2 symmetric matrices. So let's see what how the set would look. So it says the matrices are symmetric. Sorry. So let's write the set representation of it. It says W3 is set of all A such that uh, A transpose A is equal to A, and A is a 2 cross 2 matrix. So you might also get this in this form. The same question in this form. It says all the matrices A such that they are symmetric and have and are of order 2 cross 2. So for in such cases, what we should do is we should start with an arbitrary matrix. Okay, so let let A be some symmetric 2 cross 2 matrix. So what happens in a symmetric matrix is A B C D. It's any arbitrary matrix of order 2 cross 2, correct? So if you just talk about this, then it is A B C D. But then you impose one extra condition to it, that A transpose should be equal to A. That means if I take this row and I project it as a column, so it should be same. Means here also I should get AB. So that means here instead of C I should take some B. Now let's try to find what is the transpose of A. So A transpose in this case is AB and then BD. So you see A and A transpose are same. So this is one of the way. And if you find it confusing, I'll tell you the second way of doing it. You just take any matrix ABCD. Okay, any arbitrary matrix ABCD. And then you say you want A transpose. So what would be the A transpose? It would be A, B, then C here, D here. And then you equate both the matrices. Okay, equate. So what you will get? You will get A equal to A, need not to write it, D equal to D, need not to write it, but you will get B equal to C, C equal to B. So basically you get B equal to C. Okay. And that you can put. So I can use my A as, okay, this is some calculation. This is irrelevant. So I can write my A as AB, then BD. Okay. So this is how you choose your A. Okay. Now this A can take any value for ABD. ABD can be any real number. Okay, so how you're going to find the basis of it? So the idea to find basis is you try to divide it into components. Okay, so one component could be, so like what we did for I'll give a short example here. What we did for x comma y, we wrote it as x times of 1 comma 0. You take one element at a time, okay, and rest all elements you put as 0, and then y times of, now you put this element as 0 and then 1. Okay, same thing we are going to do here also. It can be represented as a, b, b, d could be written as, first let's just take a. So if you take a out, it becomes 1 here, and rest of the things let them be 0. Okay. Then you just take b out. So b out means this and this will become 1 and rest will become 0. Then you take c out. So if you
D.
no c, d out. So the moment you take d out, it becomes 0, 0, 0, 1. Okay, so here what we were saying that our basis in this case was, 1 comma 0 and 0 comma 1. Like, we do not take the coefficients, right? So similarly, the basis in this case is going to be this. First is 1 0 0 0, and then the second one is 0 1 1 0, and the third one is 0 0 0 1. Okay, and then if someone asks you about the dimension of W, okay, so dimension of W2 is W3, number of elements in your basis, cardinality of your basis, which is 3. So dimension of your basis is 3. Okay, you can say from here also, because you have 3 independent components.
Okay. So actually, I thought it's a symmetric matrix. I can write it as it's like if I'm folding. I mean, the A, D, and B, C can be same number in symmetric matrix.
Yeah.
But
So
it's in dimension it will be 2, no then, and I can write D as A also. In symmetric, it's that condition. It's okay.
no, but you need to consider all the matrices, right? If you put A here, it would still be a symmetric matrix, but
Yeah.
it will not encompass all the symmetric matrices. Okay, but this is more general form. This will encompass any symmetric matrix, because D can be equal to A and cannot be equal to A. So, but if you put A over here, that would mean that if A not equal to D, then it cannot be a symmetric matrix, which is not a case.
So maximum possible we have to take.
Yeah.
Possibility.
You need to take the most general way.
Okay.
Then it says some bases are given, and you need to find the basis for these things. Okay, so more problems, similar problems. So see, this problem is, this time it's Q symmetric. Where were we? 3. So this time it's skew symmetric matrix. What I can write? What should I take as? Okay, so again, let's start with some name, which we are taking
0
A, B, C, D.
-1.
Yeah, just to give some idea, 8 minus of A transpose, I'm writing it as minus of A, minus of B, minus of C, minus of D, and then you equate. Okay, so you get A equal to minus A, that would mean A equal to 0. You get D equal to minus D, that would mean D equal to 0. I'm telling a more general approach, though this is a good
Okay.
fact to keep in mind, that all the diagonal entries of skew symmetric matrix is 0.
0.
And then what you have
B
B
minus
equal to
C.
minus C. So maybe we can put C equal to minus B somewhere. and then it's equal to minus b. So it's the same thing, right?
Correct.
So thus we get our A as 0,
0.
b minus b, and 0. Okay. So now from
Yeah.
here, we know that it's very easy for b belongs to R. So dimension is going to be 1 only. And even if you try to write the basis, because I can represent it as 0 b minus b 0 could be represented as b times of 0 1 minus 1 0. Okay, so you are taking one variable out at a time, and there is only one variable. So this is going to be my basis. Okay, so the basis is, this case is what? 0 1 minus 1 0, a set containing this matrix.
Actually, inside minus 1 is no problem, right? Minus 1 plus 1. Hello?
Scalar times this matrix is also going to be a basis only. Okay, so you can
Okay, okay.
represent the same thing as 2 minus 2 here. Okay, so you have multiple representation, and one such representation is used over here in B2. So the basis in this case is B2. Okay, moving on to the next problem, where we have W2 as the set of 2 cross 2 matrices such that the sum of entries in each row is 0. This is going to be the fifth one.
So just adding this row and getting this 0.
So it says W2 is the set of all 2 cross 2 matrices such that the sum of entries in each row is 0. Okay, so usually what happens is, if I take any 2 cross 2 matrix, it is A, B, C, D. Okay, but it imposes an additional condition such that A plus B equal to 0, and uh, and C plus D equal to 0. Sum of row is 0. So this gives me A equal to minus B, and then D equal to minus C. So here maybe I can put A minus A minus A, and then C minus C. Okay, for all A comma C belonging to R. Then what? So what will be the basis? The basis is going to be, I'm trying to write it directly this time. Okay, so if you take A out, it will become 1 minus 1 0 0. Correct? And if you take B out, it will become 0 0 1 minus 1. Okay. Right, so this is the basis. Now if you want, you can multiply minus 1 over here. This will become minus 1, this will become 1. Okay, so any k times of this and comma any k times of this is going to be the basis. So let's check the options here. The first one, if you check, so what it does is, it says if you multiply 3 to this one, the first component, it will become the first component over here, and if you multiply minus 5 in this case, it will become the second component, right? So it's B1 is the answer here, beta 1. And then okay, how many questions are there? And W3 says it's a set of all 2 cross 2 matrices such that sum of diagonal entries is 0. This time we need to make the sum of diagonal entries is 0. So we can write, what is it, 6 na? This time let's write it directly. So my A would be what? W3 is the set of matrices, sum of diagonal entries is
Minus
0.
A. Sorry, A
So this is
minus A. B minus B. Yeah.
This can be BC. Okay. So for A, B, C belonging to some real number. Okay, that means what? The dimension is going to be 3. And if I want to write the basis for it, it can be, let's take A out, so it becomes 1 minus 1 0 0. And then you take B out, it becomes 0 0 1 0. And then you take C out, so it becomes 0 0 0 1. Okay, this is the basis. So this matches with here. Okay, this 1 minus 1, some constant times 1, and then some constant times 1 again. This was our B3. And then we move to the next question now. And the next question says that you have a matrix, has find the value of A so that alpha, so that it has infinitely many solutions. So we
The
come to
determinant 0.
question 8. So if we call it question 8, we can have our 9th question here. Okay, so the 9th question we have. Okay, it should have infinitely many solutions. So infinitely many we have already seen this has only two possible cases. One, given if A is given A is a square matrix, given A is a square matrix, it can have only two cases. First, if A determinant not equal to 0, then unique. And then if determinant of A is equal to 0, then we have infinitely many solutions. Okay. Just a second. We have infinitely many solutions. Am I audible, right?
Yes.
Okay. Infinitely many solutions. So what? So this wants infinitely many solutions. That means we can equate determinant of A with 0 in this case. Okay, so you just find the determinant of the matrix and equate it with 0. Let's do it. 1 minus 2, 1, 0, 3, 4. And then you have 5 minus 4 alpha. Okay, so if we find the determinant along the row 1, that gives us 3 alpha plus 16, and then it's 0, and then 5 times of minus 8 minus 3 minus 11. I'm assuming it is correct. Okay, so in the next step we have we are equating it with 0. Okay, so in the next step we have 3 alpha minus 55 plus 16 is minus 39, I guess, and that gives us alpha equal to 13.
13. Yeah.
Check the calculation mistake once, please.
That's correct.
Okay, so let's have 13 over here. That's the answer. Moving to the last question for the day, we have this. Let's take the next page. This was 9th question. Let's call it 10th one. So it says you have a matrix and you have a system of linear equation. Find the value of B if the system has infinitely many solutions. Okay. So we need to find the value of B. How can we do that? So we just need to find the equations and the values corresponding to it. What could be the way? What could be the way? The easiest one. There are many. So you can just start solving the equations and 1, 2. Okay, no. 4 minus 3 if I add, subtract this. Okay, no issues. So we'll have to find the solution only. That is the case with us. So let's solve the system of linear equations. So we know how we do the Gaussian elimination, right? So Gaussian elimination we are going to do 1 minus 2, 1, 2, 1, 0, and what was it? Minus 3, minus 4, 1. And then you have 3b1. Okay, let's, what can we do next? Which 0 can we make? So let's do R3 minus R1.
Yeah.
So this will make 1, 2, minus 3. Then we have 3 over here. B minus 2, 1, minus 4. And it is 0, minus 2. And what?
No, R3 minus R1. We should do R2 only, no, first.
Anything you can do, it's your choice.
Okay, one by one I supposed to. Yeah.
And 4. And here we have minus 2, I guess. Okay, R3 minus R1 is giving us this. And now maybe we can try to R2 plus 2 times of R1. Okay, let's do this also.
Actually, I tried by the algebraic method.
The scene is if it has infinitely many solutions, right? So we will try to make this row 0. Okay, because what when you have an infinitely many solution, when you have 0, 0, 0, and the component over here is also 0.
Okay.
So the same thing we'll try to do. So our task is to make one row as 0. So, okay. So now let's try to do something like R2 plus 2R1 maybe. So 2 times of R1, this will make it 0, this will make it 5, and this will make it 12. Oh, sorry, minus 6, minus 4, minus 10. Okay. And now we have 0, minus 2, 4. Okay. Now we'll do it. Let's see almost the same ratios. There's 3, 3. What we did? B plus 6 and then minus 2. We did this, right? R2 plus 3 times of 2 times of R1. Yeah, correct. So now it's easy. You say from this row, from R2, you are adding 5 by 2 times of R3. So that will make it 0. 5 by 2 here will give you 5 and then 0 again. Yeah. 0 minus 2, 4. And here you have minus 2, here you have 3, here you have 1, 2, minus 3. Here it is B plus 6. And what was it? Plus 5 by 3, 5 by 2 times of minus 2. So it is minus 5. Mm, minus 5. This is
Yeah,
correct.
correct. Minus 5.
Okay. So that will give us B plus 1. So what we know, if you have a 0 row over here, so for infinitely many solution, for
Equal to minus 1.
solution, this should be equal to 0 as well. For solution to exist, this must be 0 as well. Otherwise, it will be a case of no solution, correct? So you write B plus 6 minus 5 equal to 0, which gives you B
B
equal to
equal to minus 1.
answer. Yeah, so that was all. If you have any doubts, you can ask.
Actually, are you taking in TA classes, Dipanshu?
Sorry,
Are you taking the TA sessions?
for which subject?
Maths too.
No, I was maths to TA in the previous term, not in this term. This term I'm doing Java.
Okay, okay. What about any mentor session of maths too? No.
No, no, I'm completely in Java this term.
Okay, okay. I just want to know. Thank you.
Okay. Have a good day, everyone. Bye.
Thanks, Dipanshu. Have a good day. Thanks for the session.